My name is Atta-ul-Latif Khawaja. Today I will discuss selected problem with their solution related to chapter 30 of Survey 7th edition. So let's start. So first problem is in Neil Bohr's 1913 model of the hydrogen atom, an electron circles the proton at distance this with speed this. Compute the magnetic magnitude of the magnetic field this motion produced at the location of the proton. This problem, according to this problem, the electron is rotating around the proton, which is centered at the nucleus, according to this problem. Okay, so uh, since electron is electrical charge particle, so the current will this will be described along with the describe along the direction along the motion of the electron. So that will be along the circular path because the current is defined as the motion number of charges passing through some specific point per unit time. Okay, so uh, actually the current in this problem, the current is along the circular path, not along the straight line, but induced magnetic field is along the straight line, which is induced due to the current along the circular path. So the direction of if we how we will find the direction if we take fingers if the rotation of the finger of right hand represent the motion of current direction of the current, then the thumb will be indicating the direction of the magnetic field down toward the inward the page. Okay, so if the electron is along this circular path, then the induced magnetic field be inward the page. This expression, so this expression B equal to mu naught I divided by 2R is for the uh, current along the circular path and induced magnetic field along the uh, straight line passing through the center of this circular path. That is totally different for, but if we consider that if the current is along the, if we consider that current is along the, if we consider the current is along, if we take the current along this and electron magnetic field is along this, the expression will be a different that will be equal to mu naught I 2 pi r. But in this case, the magnetic field will be along this circular path, and induced magnetic field be along the circular path, and the current I will be uh, along this straight line. But this expression is totally different than this expression. This is for induced magnetic field along the circular path and current along the uh, thin straight wire. But this problem, the problem one is in contrast, is related to the current along the circular path and induced magnetic field along the straight line. So this B will be equal to mu naught I 2R. As we know that the current this I will be the current is representing by the charge per unit time, and as we know that uh, velocity uh, as we know that velocity is displacement per unit time or speed is distance per unit time, and time will be equal to as t will be length per unit volume, and from here the time will be equal to 2 pi. L will be length of the length along the current, total length along the current. So the length of the this circular path or current path is representing by the circle, is along the circle, and the length of the circle circumference of circle is always equal to 2 pi r. So that's that here r is the radius of this circle. Okay, so here will be a v. So 2 pi r over v. Okay, sorry, this r is same as I must write. This is actually r is same as r. Uh, that is, please note. Okay, actually both are the same. This is a typing error. So I must write this will become so the t will become a 2 pi r over v. So when we put this value of t, this will become lv 2 pi r. So when we put this value of I, that is the value of I put this value of I here. Then and by putting these given data in this expression, the result will be using the calculator, we may find this result magnetic field will be 12.5, and this will be invert the page. Okay, so next problem is problem number 2. Calculate the magnitude of the magnetic field at point 1 centimeter from the long thin conductor carrying the current. Now, this problem is different than this problem. The problem number 2, this is problem number 2. Okay, this figure is for problem 2. In the problem number 2, the current is along the straight thin wire, and induced magnetic field is along the circular uh, path of radius r. Okay, so okay. So s- so now the expression will be different. No, so the expression for magnetic field will be representing by this expression, because now the current is along this and magnetic field is along. So that's why this will be equal to mu naught I and 2 pi r. Mu naught, we know that the value of the mu naught is 4 pi 10 raised to power minus 7. I is given, that is 1 ampere, and 2 pi r is uh, 100 centimeter. So as we know that 100 centimeter is equal to 1 meter, because uh, centimean 10 minus 3. Okay, oh sorry, 10 minus 2. So that's why that will become so 100 and power minus 2, that will become 1. Okay, so by getting putting this value and computing, we will get this result. Now we move toward the problem 3. Okay, the for problem 3, uh, I have the recorded lecture separately, because I have explained uh, it briefly. It need a brief explanation. I have made a separate video, and link of this will be appearing here, or will be given at the description. Okay, the problem number 10 is also a very important, and it need brief discussion. So the separate video is of this problem is also shared. The link of this link of the solution of this problem is shared in the description. And separately video related to this problem is available on YouTube. Now the If the no the problem is about the 23, the four long parallel conductor carrying equal current, figure this and view of the conductors, the current direction into the page at A and B, because this cross representing the tail of arrows. So it means the current is invert the page at A and B, okay, and out of the page at C and D, because dot is represent dot always represent the head of the arrow, mean that will be out of the page. Okay, so the out of the page at calculate the magnetic magnitude and the direction of magnetic field at point P. Point P is at the center, locate at the center of this so and distance between these 2 point is 0.2 meters. Okay, this problem is related that every the current is along the straight line and the magnetic field is producing in a circular orbit, as in the case of one. Okay, so the magnetic field will be produced not it is the same as the problem related to the two. Okay, problem two, in which the current is along the thin wire, and magnetic field will be along the circular cylindrical symmetric. Okay, so induced magnetic field will be a cylindrical symmetric. So in this case, the and this problem is the same as the problem of problem uh, related to two this. So this the same expression will be used there. Okay, uh, so the b will be equal to at b at a will be mu naught mu naught I 2 pi a. Okay, this a is here the or radius of this cylindrical orbit, or distance from. Okay, since the each wire in distance p is making angle 45, so that will be a the distance from the so the each wire is distance from p will be uh, uh, the this length, and they are making angle 45, so that will be distance. This distance will be a, as we know that if then if this is a theta, then uh, sorry, this is true length, is this if this is making angle 45, then okay, actually sorry, no, actually this is point A. Okay, this is point C, and this is P, and so angle between them is 90. Okay, and if this is a 2, then this will be a 2 cos theta. So this AP will be distance of P from A point, that will be equal to uh, 2 sorry, if this is a 0.2, then it will be a 0.2 cos theta. So this will be 0.2 cos, and this is angle 45. Theta is 45. So So this will be the this result. So this AP will be the distance of may say that the distance of AP will be 0.2 cos 45 if this angle is 45. So this distance will be okay. So this will be and this will be a 0.2 mm. Okay. Uh, so here this will be the R, and this AP is actually the R. This is R. Okay. So that's why this will be this is AP. Okay, and that is equal to R. Okay, so by putting this value, this will be magnetic field due to A point. Similarly, we will find the magnetic field for the C, the same that will be, and that will be for B and D. So that will be, and they because they are four-current, and so they will be, and they are making angle 45. When we take a projection along this, that will be the sine 40 of why? Because when we add in description, I have explained that because the all the direction will be sum of on this, and that are the making the sine 45. So when we add up with 4 time and taking angles, so this will be a result. Okay, and this if you take consider the right hand rule, and at every point will be enforcing the magnetic field toward the bottom of the page, mean downward, because that will be along the this. So this will be the result. Okay, the next problem is related to the problem number 25. In problem 25, the page 30 problem figure is 30.25 is cross section view of the coaxial cable. Mean they are this is the cable which have two two conductors, conducting cylinders. Okay, the center conductor is surrounded by the rubber layer, mean they are isolated from each other, which is surrounded by outer conductor, which is surrounded by another rubber layer. In the particular application, the current in the inner conductor is 1 ampere out of the page, because here is dot mean the outward of the page, and cross mean cross represent the tail of the arrow, so it's mean it will be invert the page. Okay, determine the magnitude and direction of the magnetic field at point A and B. Since at since the again this is problem number 2, like 2, the current is along the straight cylindrical cylinder, straight wire cylinder. Okay, wire or a cylinder. Okay, conducting cylinder. So current is along the straight line, okay, or a straight cylinder. So magnetic field will be produced, will be a cylindrical symmetric, okay, and that will be obey the formula B equal to mu naught I over 2 pi r. Okay, the same as so B equal to mu naught I a mu naught I a 2 pi r a, where I a is the current through the area of the circle of radius a. Because that is will be a, in a cylindrical magnetic induced magnetic field will be a cylindrical uh, symmetric, and we must be covered the the current which is producing this magnetic field. Okay, so the magnetic this, if we consider the cylindrical cylinder which surface is passing through the this point A, will be covered only this central conductor of 1 ampere conductor. So this magnetic field will be produced at induced magnetic field produced at A will be only due to this uh, this current that will be that is equal to 1 ampere. Okay. So using this for expression, we will get this result. Mu naught is equal to 4 pi 10 raised to power minus 10 minus 7. I is 1 ampere, 2 pi, and radius is given 1 millimeter. Okay, 1 millimeter mean 1 10 raised to power minus 3. Milli is 10 raised to equal to 10 minus 3. So by putting all these values and computing, we will get this result of magnetic field, okay, toward the top of the page. Mean that will be actually that will be if we are considering the current along this will be anti-clockwise. Okay, if the out of the page, then current will be along the anti-clockwise. And for B shape, when we consider this uh, this outer cable, every conductors are inward the here they are 1, 2, 3, 4, 5, 6, 7. Mean these are the this is the this cylinder is inside, not 1, 2, 3. Sorry, I'm wrong. So this is the outer hollow surface containing the charge, and the current is inside the page. So the magnetic field will be produced along the clockwise for this that will be anti-clockwise, and that will be for outer surface, that will be a clockwise. Okay, using the right hand rule. If thumb is indicating the direction of the current, then rotation of the magnetic rotation of the fingers will be representing the direction of magnetic field. Okay, one will be for this, because the thumb is upward, so that will be anti-clockwise. Okay, because rotation of the fingers along the anti-clockwise, so the direction of the magnetic field will be anti-clockwise. But for outer surface, the current is inward, so that will be for outer surface mean 3 ampere current, that will be along the along the clockwise, so that will be a clockwise. Okay, so similarly for B for point B, that will be clockwise. Okay, magnetic field clockwise. And this is this B point is covering the current due to no, sorry, this point B, at point B there are two current, not only due to this B. If we consider the cylinder around this point B, because the magnetic field will be cylindrical symmetric due to cylindrical conductor carrying current. So the magnetic field will passing through the point B will be cylindrical symmetric. So and it will enclosing the this 1 ampere current and this 3 ampere current too. So this magnetic field will be induced due to both of the current. As if we consider if we consider outside current positive, then inside current will be negative. So if we consider that outside current out of the page, uh, Actually, I'm interested. If we consider that out of page current positive mean out of current is 1, if we consider that is 1, and inside page current is negative, that will be, if we say that, if we consider that is inside is -3, then total current will be 1 plus 1 2, that will be 1 minus 3, that will be a -2. Okay, mean if we are considering that the inward is mean 2 inward. Okay, because negative mean inward, if we considering that inward is negative and out of the page is 1, because result is negative, so this negative will represent the inward, but in inverse, but in inverse out, if out I consider that out is negative -1, in is positive, then that will be 3 will be a positive. Okay, and I will be equal to uh, uh, -1 plus 3, that will be a +2. So so as so again, if 2 is positive, if we are considering that positive is in, so 2 will be again inward, so this positive 2 will be represent the inward. So I want to actually explain that if you are considering this representation, even the current result, net current will be 2, will be inward. If you are considering this red red representation, even then the result will be a 2 ampere and it will be inward, because in this case you are considering the inward is negative, so result is also inward. Okay, so that's why that will be a 2. In this case, if you are considering the inward is positive, then result will become is a positive, mean it will be represent the same result, that the 2 ampere current will be inward. Okay, so this will be so net current will be a you may consider this result or this result. So the magnetic field, by putting these value in this, because the this 2 value in now the current for instead we will put the value 2 ampere in the this expression. Okay, so this will become this actually expression is again I must write b equal to mu naught uh, mu naught sorry mu naught I 2 pi r. Okay, so this is the result. Okay, the next problem is okay, sorry, the next problem is that if the problem is 35, what current is required uh, in the winding of the long solenoid that has 1000 turn uniformly distributed over the length of 0.4 meter to produce the center of the solenoid magnetic field of magnitude this. We know that we have already derived this expression. So B equal to mu naught N I L. And so I, we have to find the I value. So I will become mu L, mu N. So by putting the value of magnetic field, that is one, that is given. Uh, so for produce the magnetic field is given. Yes, that is magnetic field. Mu naught is 4 pi 10 raised to power 1000. Number of ton is 1000. So by putting these all value, we will get the required result. That is a very straightforward result, 31.8 milliampere. If you have any question and or feedback, it will be highly appreciated. Put your question in the comment box. I will definitely try to answer your question. Thank you very much. And the link of unsolved problem, video link of solved problem, which related to problem 3 and problem 10 is given uh, at the description, as well as it will be pop up here. Okay, inshallah. And here. Thank you very much. Allah Hafiz.